My name is Bob Cebelak. I'm here in the physics department of Grand Rapids Community College. I'm speaking tonight with Dr. Ron Mallett, who's a guest tonight from the University of Connecticut. He's here to tell us about his work, which involves the physics of time travel and many other exotic things. So we're glad to welcome him here to our campus.
Thank you.
First, I'd like to note, everybody knows that time travel is a crazy notion that can't possibly come true, that people have fantasized about for a long time. Yet, you have the notion that somehow this is going to be possible within a reasonably short time.
That's right.
And you've got some crazy theory that this whole thing is based on.
Well, it's actually not based on a crazy theory, but it's based on solid work of scientists that I think everyone is familiar with, and that's Albert Einstein. And in fact, that's what makes it a solid physics. And the thing is that what most people don't realize is that we actually have been able to send things into the future already based on his work. And what we're on the threshold of doing is understanding how to send things back into the past. But all of this work is based on that solid foundation of Einstein's theories of relativity.
In fact, all of your work up to this point essentially has been working with general and special relativity.
That's right. That's right. And there's a short distinction between the two. I mean, I can just put the two in a nutshell. Einstein said that if you speed an object up, its clock will slow down. Time for a moving clock will slow down. So special relativity actually says time for a moving clock slows down. The general theory of relativity is about gravity. And in a nutshell, it says that, according to Einstein, gravity can affect time. So those are the two basic theories. One is about light and the other is about gravity. And my work is based on Einstein's general theory of relativity.
The special theory of relativity is something we occasionally talk about in introductory physics classes, but the general theory of relativity is known to be a complicated theory of which there are more than 10 or 15 people in the world that can deal with it, but there are not too many people that have come up with solutions and answers to models. At what point in your life did you start working toward learning enough to be able to do what you're doing with the theory of relativity?
Well, the thing is that it actually started out a long, long time ago as far as my interest in the theory was concerned. I actually was interested in the theory because of a tragedy that happened in my life. When I was 10 years old, my father, who was the center of my life, he was a television repairman in the Bronx in New York. And the thing is that to me, he was indestructible. What we didn't realize as children is that he had a weak heart. And he died of a massive heart attack when he was only 33 years old. And my world was devastated. I mean, I just was inconsolable. The thing is that among the gifts he gave me, which was gyroscopes and crystal radio sets, was a love for reading. And about a year after he died, I came across a book that changed my life. It was H.G. Wells' Time Machine. It was what's known as a Classics Illustrated version of it. The thing is that in that, it said that scientific people know very well that time is just a kind of space, and we can move forward and backward in time just as we can in space. And when I read that, that was the thing that you might say saved me psychologically, because I thought if I could build a time machine that I could go back into the past and see him again and maybe save his life. And so that actually became my passion, my goal, to try to build a time machine. As a child, I even tried, doing it with vacuum tubes and all this other equipment that my mother kept after my father passed away. Of course, nothing happened, but I realized that it said that scientific people know very well. So I knew that must mean that you had to look at science for it. Then that's when the second person, in a sense, came into my life. A couple of years later, I came across a popularization of Einstein's. It was called The Universe and Dr. Einstein by Lincoln Barnett. And even though I couldn't understand all of the articulation in the book, I did understand enough that it said that according to Einstein, time can be affected. And so I tried to understand as much as I could, but I realized that eventually I was going to have to learn more about science. And that was going to be a problem because after my father died, we were poor. I mean, we actually plunged into poverty, and so college was not something that was going to be automatically in my future. As a matter of fact, after I got out of high school, I joined the Air Force. This was during the Vietnam War era as an enlisted man, and I worked as a computer technician. And I wanted to save up the money, but I was able to use the GI Bill in order to go out and to actually get my bachelor's and master's degree at Penn State University. And I was fortunate enough to do well enough that I had a National Science Foundation traineeship for my PhD work. But the thing is that I learned that more and more when I learned about Einstein, I learned more and more about the nature of time. And eventually I realized that according to Einstein, since you can manipulate time by speed, you could actually begin to send things into the future. That is to say that if you are actually moving fast enough, then time slows down for an object. And of course, I mean, when I talk about time, I'm not talking about just clocks associated with mechanical mechanisms. Your heart is a clock, okay? So this means that if you travel fast enough, your heart rate would actually slow down. You would actually age less than other people. Now, people might ask, wait a minute, has this been shown? Not only has it been shown, but it's actually something that we see every time they turn on. There's a device in Switzerland called the Large Hadron Collider. This is a particle accelerator that accelerates particles close to the speed of light. Normally, some of these subatomic particles can only live for a fraction of a second and they completely disappear. But what happens is that when they turn the machine on and accelerate these particles, they actually find that they can get these particles to live 10 to 20 times longer than they normally would. Okay? This means that with respect to other particles, they're actually traveling into the future. So we actually have been able to do it with subatomic particles. We can even do it on a human scale. As it turns out that an experiment that was done back in 1971 in which they had atomic clocks, which, as you know, are the most precise timekeeping mechanisms that we have. They put one of the clocks on board an ordinary passenger jet, and they kept the other atomic clock at rest at the Naval Observatory. When they flew the passenger jet around the world close to the speed of sound and brought it back, they actually found that the clock, when they checked, that had been on the passenger jet had slowed down. It had actually lost time. Now, it was only by fractions of a second because the speed at which the plane was moving was the speed of sound. That is slow compared to the speed of light. The speed of light is 186,000 miles per second. The speed of sound is about 720 miles per hour. Now, it's hard to grasp sometimes how slow that really is compared to the speed of light. But you know, the speed of sound sometimes is measured in what are known as Mach numbers. 1 times the speed of sound is Mach 1, 2 times the speed of sound is Mach 2, and so on. We have passenger jets that can do Mach 1. We have fighter jets that can actually do Mach 2. And we have stealth fighters that can go Mach 3, 3 times the speed of sound. Now let's put the speed of light in terms of Mach numbers. It turns out that the speed of light travels at Mach 1,000,000. Okay, in other words, 1,000,000 times faster than the speed of light. As far as sound is concerned, the speed of, as far as from the light standpoint of light, sound is practically standing still. So when we have rockets that can go close to the speed of light, we'll see time slow down, not just in terms of fractions of a second, but in terms of years. This will actually mean that future astronauts who are traveling close to the speed of light will actually be traveling, they'll be time travelers, they'll be traveling into the future. And we've actually really seen the baby steps of this already in our time. So, but that's time travel into the future. What I was interested in was time travel into the past. And that's something else because you can't go back into the past no matter how fast you go. Light is the speed limit of the universe, if you will. And you can't go faster than that. So there's nothing that you can do as far as speed to go back into the past. But it turns out that there is another way. And this has to do with Einstein's second theory. I should mention that his first theory he published in 1905. It took him 10 years to develop the second theory. And the reason why it took him 10 years was he had to learn a whole new set of mathematical techniques in order to do it. They're called the tensor calculus. And he actually had to have a mathematician friend of his help teach him the different techniques that he needed to do it. The thing is that eventually he developed the theory. And the reason why he developed it in the first place was because of the fact that all the other forces in nature seemed to obey the speed limit of light, but gravity didn't. Gravity, according to Newton, could actually go faster than the speed of light. So Einstein said he had to develop a new theory of gravity. And when he did, he found that something strange happens to time. It turns out that according to Einstein's theory of gravity, which is called the general theory of relativity, time slows down the stronger gravity is. For example, that means that a clock here at the surface of the Earth, where gravity is strong, will actually slow down compared to a clock at a higher altitude. Okay, now, once again, you might say, wait a minute, has this effect of gravity on time been seen? Not only has it been seen, but what people don't realize, that it's actually part of our everyday life. What do I mean by that? The GPS system, okay? It turns out that the GPS system, its accuracy relies on taking Einstein's theory into account. Here's why. The thing is that when they were setting up the GPS system, the way in which it works is that right now, about 12,000 miles above us, there are 24 satellites that are in geosynchronous orbits. That is to say, there's a satellite covering a particular portion of the Earth at any time. At a certain time, a satellite sends a signal which reaches the unit in your car at a certain time. Okay? Now, the thing is that in physics, in fact, it's something that's a part of elementary physics, is the fact that if you know one of three things, there's a relationship between distance, speed, and time. So if I know any two of these, I can determine the other. So for instance, if I know the time and I know the speed, I can determine distance. And that's the way your GPS system works. That is to say, we know the time the satellite sent the signal and the time that it reaches your unit. We know the speed of the signal. It's the speed of light. So we can compute the distance. But however, when that system was worked out, it was giving the wrong locations. I mean, the locations were all over the place. And it was because the engineers had initially forgotten to take into account Einstein's theory of gravity, because the unit in your car, where gravity is stronger at the surface of the Earth, is actually running slower. The clock is running slower than clocks on board those satellites. Those clocks are actually running faster, so the systems were out of sync. So they actually have to use computers to calibrate the system to take that into account. So we really do know that time is affected by gravity, and that's what my work is based on.
It's a small correction, but a noticeable and known one.
It's a noticeable one, and
Yeah.
it's something that we need. So these things are based on real scientific fact, and my work is based on that, okay? Because one of the things that Einstein's theory also says, which is different from Newton, according to Newton, the only thing that can produce gravity is matter. For instance, the Earth creates gravity, which keeps us anchored. The sun has a gravitational field which keeps us in orbit, the Earth in orbit around it, and so on. But in Einstein's theory, not only can matter create gravity, but light can create gravity, okay? And the thing is that that's where my breakthrough came in. In fact, the logic of it is pretty simple. We know that gravity can affect time. And if light can create gravity, then that means light can affect time. So by using light, we can actually manipulate time. And that's what I realized, is that by using light in a certain way, you could actually manipulate time. And the way in which you can do that is by using a circulating beam of laser light. And that's what my theoretical work was based on, was actually showing that you can actually create a mathematical model in which you can actually show that by using circulating laser light, you can actually twist space and you can actually twist time into a loop, which could allow you to go back into the past. So that was my work. And as I said, the thing is that it's accepted, the theoretical work is accepted by my colleagues because it's anchored in Einstein's theories.
And indeed, the work you did involved modeling a system using general relativity, coming up with the answers, which took multiple equations, 10, 15?
It took a lot. I mean, the thing is that, you know, it's just interesting in the public when the word theory, colloquially for people, actually means like, oh, I have an idea. For physicists, having a theory means a whole different thing. It means that you actually have a mathematical model that can actually make predictions that have the chance of being verified experimentally. And yes, coming up with the equations to actually show the twisting of space and time was a tremendous intellectual labor on my part. And the thing is that, but I knew that I had it right whenever I finally did it after many, many, many missteps. And the thing is that when I presented it to my colleagues, I knew I had to make sure that it was right, because if they saw any errors, as you know, physicists are not, psychotherapists. They jump in right there and tell you, straight away.
They're quite famous for letting you know when you've made a mistake.
Exactly.
Yes, indeed. Yes, indeed. The thing that I found most interesting about your result, of course, is that indeed you do have a twisting that you've calculated going on. And beyond simply calculating it, it seems to be a measurable sort of thing. That is, it will not be a, boy, theoretically, I think this might happen story. This is something that experimentally you hope to also.
That's right. In fact, that's the other thing that's important to realize, is the fact that in physics there's a sharp division of labor between experimental physics and theoretical physics. I came up with the basic equations that show this, but there's the experimental side of this. I mean, Einstein, for example, came up with equals mc squared, but Einstein did not build nuclear reactors or wasn't involved with the bomb project. And it's the same thing with my work. I'm a theoretical physicist, and I have an experimental partner. His name is Chandra Chowdhury, and he's not a relativity theorist, but he's a laser physicist, and he became interested in my work. And so what it is that we've come up with some plausible experimental designs, and what we're looking for right now is the funding to do that. That's the other thing that the public doesn't realize, that for the theoretical side, all it required was mental power. And that didn't require funding, okay? At least direct funding, I should say. Indirect funding, because I was a faculty member and that was being supported that way. But as far as funding, but for experimental equipment, this can run into hundreds of thousands of dollars, and all the way up to, like, for instance, the Large Hadron Collider in CERN costs $10 billion. So that's what we're trying to do right now, is to get the funding that would lead to the experimental results that we hope to find.
As I understand the experiment, or at least one of a couple proposed ones, it involves rotating the polarization of either a neutron beam or light itself, perhaps.
That's right. That's right. That's a very good point. The thing is that one of the things I predicted, for instance, is that a circulating light beam will cause a twisting of space. And if you think, for instance, of the water in this cup as being like empty space, and you think of a spoon as being like circulating light beam, then as I stir the water starts swirling around. That's what happens to empty space with the circulating light beam. Okay, it starts swirling around. Now you might say, how do I see that? If it's empty space. Well, the thing is that what I propose was that if you put a particle, a neutron, which is part of every atom, into the space, then the neutron a neutron spins like a little top, okay? And so if you put it in that space, the space is being stirred around, the neutron spin will get actually swirled around. And so you'll actually know that happens, and that's one of the things that we're proposing. That seems to be one of the most promising aspects. We've looked at doing it with light on light, but it seems like looking at how a neutron is affected is going to be the most promising from an experimentally observable standpoint. So that's one of the things that we're looking at. And one of the things that we're trying to approach it with is getting funding from crowdfunding, which is a now popular way with programs like Kickstarter and things like that. And at the University of Connecticut, they're having their own version of that. And I know that the public is very interested in what it is that I'm doing, so we're hoping to try to get the funding via that channel.
In truth, as I understand it, although all physics experiments are expensive, this doesn't seem like necessarily a tremendously expensive experiment.
Not for the space twisting portion of it. The thing is that what we need is what they call a proof of concept, which means doing the modeling in a precise way to see whether or not you get the right numbers. Probably about $250,000 would be needed for that. But that's just the proof of concept. Once we start, building the equipment, it probably will go into a few $1,000,000 at that particular point. But that's still modest compared for experiments in physics. Now, to go beyond that, with twisting of time, because the thing is that in Einstein's theory, whatever you do to space also happens to time. What we're not conscious of this, but we all move along a timeline from the past to the present to the future, all of us, okay? The thing is that if space can be twisted strongly enough, okay, then what will happen is that timeline could actually be twisted into a loop. So imagine if you have this line of time from the past to the present to the future, and you twist it into a loop. You could go from the past to the present to the future, but you made time a loop, so you could go from the future back into the past. But the energy that's required for that is gargantuan compared to the energy just to stir space. And now we're talking about the type of money that would probably be on the order of what was for the Large Hadron Collider.
That would be expected. Experimental progress, that is the proof of concept?
Well, right now we have to get the funding for the proof of concept, and that's where it is experimentally at the moment.
Okay. Done at Connecticut or Penn State?
Oh no, this is actually at the University of Connecticut. Okay, that's where we're trying. Although we might be able to link up with the National Institute of Standards and Technology, because they actually have neutron facilities. As a matter of fact, in January, I visited the it's called NIST, National Institute of Standards and Technology. It's actually one of our important institutions in this country because they actually set up our standards for measurement of time, distance. And the thing is that they were interested in what it is that I was doing. But once again, they would like to see more as far as, the concrete, numbers associated with it. Mm-hmm. So that's where we are with them right at the moment.
Theory first, check first result, go for something bigger.
Right, exactly.
Time travel from a physicist standpoint is something that is believed in to the point where I have a quote from a Brian Clegg book that it would seem, unless our current theories are incorrect, building a working time machine is only a matter of time. I know you're on the really optimistic end of that.
That's right.
Based on your
Based on my work, but the thing is that, and this is an interesting thing, when I started in the field, I actually kept my interest. When I say started, I'm talking about as a child and everything like that. And time travel was something that people did not, was even within the scientific community. Even now, physicists, they use a code name for whenever they're publishing their papers. They don't call it time travel. What they call it is closed time-like curves, okay, which is exactly the same thing. So if you're reading a paper by Stephen Hawking or one of the other physicists, they'll be talking, and they say closed time-like curves. They're actually talking about time travel into the past. But now there are other physicists who are looking at other processes. For example, there's a man it's at Princeton, and he's working, his name is Richard Gott, and he's looking at what are known as cosmic strings and how these might form these loops in time. And then there's a physicist at Caltech, Kip Thorne, who's looking at the possibility of using wormholes to do that. And then I'll actually be talking more about Kip Thorne's wormhole idea. So the thing is that now a lot of physicists are looking at it. My work was the first to suggest using light to actually manipulate time to go back in time. So that was my major contribution to this particular area.
Although I think I'd add something else as well, is that much of the public's disbelief or doubt in this is that many of the proposals sound as though we'll take a wormhole here and a wormhole here and we'll spin them around. And then when you ask, well, where are we going to get this wormhole and how's that going to work? Your work since the beginning has been much more on a personal level.
Yeah, that's right. As a matter of fact, the book that you mentioned by Clegg, he actually talks, in fact, he devotes an entire chapter to my work. And I think the reason why it has caught the public's attention, as well as the attention of some of my colleagues, is because of the fact that it's based on something that we could do in the laboratory, and it's based on something in which we actually have control of, light. And lasers are something that we're very able to manipulate. So it brings it into the realm of seeing, this might be possible, but yet it's anchored on the solid physics of Einstein.
Excellent. As we run a little bit low on time, I'll note that Time travel to many seems quite impossible. But if I was to guess, having a 12-year-old poor son without a father, family in poverty, you went to live, as I understand, with your grandparents, had to move from where you lived, to go from that beginning to where you are in the study of physics is a remarkable accomplishment. How did you find the determination to work through as much as you did? Was it just the motivational factor?
That was the thing. It was the passion to see my father again. That really was one of the things that set the stage for me, because I really had this unquenchable passion to see him again. Also, I should say that along the journey, I really developed a fascination for physics in itself. I mean, I actually fell in love with quantum physics, with trying to understand the mysteries of the universe. So, in a sense, even though my original passion started there, the subject, in a sense, fed on that in itself. And so I was able to become fascinated with other aspects of it. Because, as you might imagine, I didn't really tell my colleagues that I was studying time travel. I wouldn't have gotten my job at the University of Connecticut. My cover story was with black holes. Black holes are strange, but they were considered to be legitimate strange. And they also, you can talk about time, you can study how time is affected by gravity by looking at them. So that was part of what I really did as far as building my career. But it was more than a cover story. I mean, I really wanted to know and understand about black holes, and I really wanted to understand about quantum physics and the mystery of the universe. So those things kept me going, okay? But this was always in the background. And it was that, but that was it. But and the thing is that one of the things I try to tell students, that as far as, trying to get to what seems like an impossible dream, is having a passion for it, what it is that you're doing, okay? And then the diligence, the willingness, the diligence to work for that. What's in between that is developing a game plan for what it is that you're going to do and how it is that you're going to do it. But yes, I mean, that drive was there in the beginning, but as I said, there were little goals along the way and other things that were associated with the field that I really loved, and that's what kept me going. And then in the book that I've tried to, the book that I wrote, Time Traveler, is actually a memoir as well as a popular science book, because I wanted to see people to see not just simply the science of the possibility of time travel, but to also see the journey that was there. And so that this journey can actually encourage them in their own journey to try to accomplish the things that they want to accomplish with their life.
Indeed, the book reads as a novel. It is extremely motivating to suggest that age 12, you had a plan, and it progresses directly from there. You note, cover story for some of the work you did, but the work you were doing was not just a cover story work. It literally laid the groundwork for where you are, and was and is legitimate research in the field.
Oh, thank you.
In a more speculative way, I think, is there still hope to achieve your main goal?
I think that there is. I'm not sure whether it will happen in my lifetime. I would like to see the beginnings of it in my lifetime. The thing is that as a theoretical physicist, I feel that I've actually accomplished what it is that I had wanted to accomplish, which is that I know how it can be done, okay? And the thing is that how also I know that there are limitations to being able to do this. But now it's gone beyond the wish to see my father again, because what I realize, and people have asked me, what other practical application would one have for time travel? The thing to me is that it could be used as an early warning device. Imagine that we had a device in which we could get information from the future that could tell us about future disasters like hurricanes and tsunamis and earthquakes, things that could save thousands of lives. To me, that in itself is worth pursuing this, because it would give us a control of our destiny that we haven't even been able to dream of. And to me, that would be worth the pursuit of it. And as I said, I have the satisfaction of being able to at least lay the groundwork for a possible solution to that problem.
Mm-hmm. In an even more speculative note, I'll note toward the very end of your book, you note that physicists are also somewhat famous for wondering about the possibility of other life out there, other areas, other areas in the universe, in this case even other universes. And you know literally that if somebody builds a time machine in some other location somewhere, that would allow us even in our era to perhaps use it.
That's right, because the thing is that a terrestrial time machine only works back to the point in which you turned it on. For example, suppose I turned it on today, and it doesn't depend on what mechanism you use, but just suppose you turned it on today. If you turn it on and leave it on, it actually creates the conditions for time travel. So if I turn it on today and leave it on, let's say for 10 years, someone could send information back or come back 7 years, 5 years, all the way back to the time the machine was turned on, but not earlier than that. That's what I meant by fundamental limitation. That means that until the first time machine is turned on, we can't go back earlier in the past. However, because of studies in the 90s, that we know that there are other possibilities for life. There are what are known as extrasolar planets. That is to say that these are planets that are orbiting other suns. And it wasn't until the 90s that we actually had real observational evidence for the fact that there are other planetary systems. We knew there were stars, but we didn't know that they had planetary systems. What we found is that some of these planets are in a location that might contribute to life. So physicists now seriously believe that the universe, since this is just in the neighborhood of our universe, and our billions, our neighborhood of our galaxy, I should say, and we know that there are billions of galaxies, this means that the universe is probably teeming with life. So if this is so, then some of these civilizations may be more advanced than we are, and they may have had started time travel, let's say 10,000 years ago. So there's the potential that if we encounter them, we might be able to use their time machine to go back to visit our distant past, so there would be no limit. There would be a limit as far as their machine, back 10,000 years. But eventually we may be able to visit ancient civilizations. And to me, that's an exciting possibility. So I think that somewhere out there in the universe, it already has happened as far as time travel is concerned, but we will eventually catch up.
Mm-hmm. But no timetable necessarily on our particular civilization catching up.
No precise timetable, because it has a lot to do with motivation. And unfortunately, sometimes we're motivated by external circumstances. And I'm just using our country as an example. If, for example, we were motivated by the Second World War to actually see that E equals mc squared. We could actually get atomic energy. If it hadn't been for the Second World War, we still would probably not have practical atomic energy. And the same thing with Sputnik is another example. So we were motivated by external circumstances. I like to say that if we found out that North Korea was working on a time machine, I wouldn't know what to do with all the money that would all of a sudden be dumped into this.
I can believe that. If anyone from our civilization, well, no, let me start this over. I would assume that someone who built a time machine successfully, or had one, certainly in this case we'd be talking about another civilization that had one on, that there would be certain people in the past that would almost definitely get a visit. And in the case of time machines here on Earth, for sure, boy, H.G. Wells. You get access to a time machine, you're going to go talk to H.G. Wells. Would somebody from a different civilization looking over the history of Earth come by to talk to you?
You know, that's a nice thought. I don't know. I would hope that they would.
I speculated that you'd had speculated about just that.
I have. And it's a fantasy of mine, and it would be something that would be really neat. But yeah, that would be neat.
I'd rather expect it so. Physics also is famous for peculiar theories such as multiple universes. And,
yes.
Time travel, we haven't even mentioned, of course. Time travel to the past is filled with paradoxes and,
That's right.
and notions such as that. One way out of it from a physicist standpoint, that's also used in many popular literature, devices, and movies, is the notion that go back in time, start, in a sense, a new universe path that would be different from the one we currently are on.
Mm-hmm. Oh yes, in fact, that's the The paradox you were mentioned is actually a very important paradox that has to do with travel into the past, because when you're traveling into the future, there's no paradox. But when you travel into the past, there's what's known as the grandfather paradox. And in the form that I like it, it's if you travel back into the past, suppose that you interfere, you keep your grandparents from meeting each other, let's say, okay? Well, if they never meet each other, they don't have your parents. And if they don't have your parents, then you don't get born. But if you don't get born, then who was it that went back into the past to start this? That's called the grandfather paradox, where potentially you could do something that would seem to erase your existence, and if you did that, then how could you go back and interfere? It turns out that quantum physics actually provides a way out. The two pillars of modern physics are relativity and quantum physics, and we've talked about relativity, but quantum physics plays a major role. And there was a physicist in England, David Deutsch, who in fact applied the mathematics of quantum physics to time travel to see what would happen. And it turns out that there's this notion of parallel universes, which the basic idea of a parallel universe, which actually goes back before Deutsch's work, was developed by a man named Hugh Everett III at Princeton back in the 50s. And essentially what he did was, when he applied quantum physics to the universe as a whole, he came up with the result that for every decision that happens, all those decisions play out, but in different universes. The example that I like to use is that suppose that today you were trying to have a cheeseburger or fish sandwich. At the moment you chose the cheeseburger for lunch, there would be a split of the universe, and there would be a universe in which you chose the fish sandwich. There would be two separate universes with two separate yous. You wouldn't know about each other. And this is happening for everyone's and everyone's. I mean, it's mind-boggling, but there would be all of these universes that would be being created. And it doesn't have to do with human consciousness. That is to say, if an electron had to take this path or could take this path, it would take both paths, but in different universes. This is called the parallel universe theory. Originally it was called the many worlds interpretation. And if you apply it to time travel, what Deutsch found is that when you go back into the past, you don't arrive in your universe originally, you arrive in the past of a parallel universe, which looks almost exactly the same as this universe. And in that parallel universe, you could do something strange like preventing your grandparents from meeting each other. The thing is that you would find yourself in a strange universe in which you were never born in that. However, when you went back to the past, the original universe was split off. That means that you didn't arrive in that original universe. So that original universe, your grandparents meet each other and give rise to you so that you can go back in time. So that shows how quantum physics and the notion of parallel universes can actually resolve this notion of the grandfather paradox. Now, whether the universe plays it out this way or not, that's something that we can only tell by doing the experiments. But it is the possibility that that parallel universes could exist, and this would resolve the grandfather paradox.
And another quote I noted from your book that I suspect I could find is that, indeed, you do believe at some point in the future we'll get a chance to find out what happens in some case like that.
Oh, yes.
Can we go back and, when we change the past, what happens?
That's right. And the thing, it's going to be interesting to see, because the
we really don't know.
We really don't know. We really don't know. We really don't know. I mean, the universe is full of surprises, and our universe is very, very strange. I mean, quantum physics in many ways is even stranger than relativity. But yet, quantum physics is the basis of our civilization. I mean, our cell phones, our PCs, all of these things are based on quantum physics. But quantum physics leads to some really strange results, like the notion of parallel universes. So it's going to be interesting to see how this really plays out once we do it.
Well, as I understand it, I believe we're out of time. I've been very pleased today to talk with Dr. Ronald Mallett. I've been very pleased to talk with Dr. Ronald Mallett and his book, Time Traveler, which I've found is an amazingly inspirational book. Not so much, I'll admit, for the time travel. Time travel is a little tough to tell, but the story behind the man's work is really quite incredible. I'm very glad you've been able to come to speak to us today, our students, and to give us this example.
Oh, thank you very much.
Thank you very much.
It's my pleasure. Thank you.